Well, welcome to our virtual class. We'll try and keep this brief, but I figure this will be the best way to continue learning things in this class as we meet kind of online like this. So if you haven't read the Google Classroom posts about what we're going to be doing and the structure of meeting online like this, then make sure that you read that first. But today we're going to jump into two sets of notes. So when you're watching this video, don't just watch it like you would some other YouTube video. Have your notebook in front of you, just like it's a normal lecture in class, to take notes and to learn new things. So pause the video if you don't have a notebook, and make sure you get that. So we're going to look at chapter 10.2 on verifying trigonometric identities. And also chapter 10.3. So 10.2, we've already done a little bit of verifying trig identities. We have looked at equations where you have one side that has a bunch of trig expressions that are multiplied or divided or added, and it's equal to something else. And you're trying to show that the left side is equal to the right side. So we've already done some work, but I want to review it. Make sure that we have a good process for looking at these problems, and then we'll practice some problems, and we will have a homework that I will ask you to do, where you can practice these problems, as well as some of the stuff from chapter 10.3. So first, what does it mean to verify or prove something? Oh, actually, secondly, one of the note is that these notes, at least the structure of the notes, is available on Google Classroom. So you can have those or download that Word document, and you can either type in that document, or maybe you can print it out and write on the side of the words or something like that. So that's another option too. So what does it mean to verify or prove something? Well, in this case, we are trying to show that these different trig expressions added together can be equal to something else that might not normally be apparent. And we're going to use our fundamental trig identities. We're going to use our reciprocal identities, the even and odd identities, the cofunction identities, and the Pythagorean identities. Right, we got like 5 groups right now, and we're going to be adding to those over the coming weeks. So first, some guidelines, things that you want to do. You want to try and work with one side of the equation at a time. So let's look at this first identity here. This is C, part C, and then the first one, part A, C dot A. And it says verify the identity secant squared of x minus 1 divided by secant squared of x is equal to sine squared of x. So what we're going to try to do using the first guideline is only change, let's say, the left side of the equation if we can. So this can be helpful just to kind of help you figure out what to do by simplifying, just focusing on one thing at a time. Otherwise, it might seem difficult to work with one side if it's too simple. Right? The side sine squared x is kind of in a very simple form, whereas the left side secant squared x minus 1 over secant squared x is a bit more complex. So you usually want to simplify down the more complex side. Okay. For the second guideline, it says look for opportunities to factor an expression, add fractions, square a binomial, or create a monomial denominator. So this is a lot of different things, but factoring can be helpful. Combining fractions, sometimes squaring both sides of an equation, or if we have a denominator that are two terms, like sine x plus cosine x, sometimes it will be helpful to create that into one fraction, so you can flip and multiply those fractions. Part C, we want to look for opportunities to use the fundamental identity. So if we can simplify things down to sine and cosine, that's helpful. If we can use one of the Pythagorean identities to simplify something like 1 plus tangent squared of x, right? We can simplify that to secant squared of x, or one of the other fundamental identities. And Part D says, if all the preceding items don't help, try converting all items to sine and cosine. Oh, okay, we did that. And the last one is always try something, right? Part of this process for solving these problems is you just want to try and do something, and sometimes it'll work out, sometimes it won't. And when it doesn't work out, you want to go back a few steps and try out something at a different spot, right? So we're trying to practice all these different tools and solve lots of different kinds of problems, which is what we're going to be focusing on today. So that's with the main instruction side of this. Let's try some of these problems, and I'll work through these. I'll give you guys some problems to do on your own for practice, and I'll post the answers to those in Google Classroom, and then I'll also have a homework for you. So first problem, secant squared of x minus 1 divided by secant squared of x is sine squared of x. Let's change the secant squareds of x to cosine first. Let's see if that works. So we can take 1 over cosine squared of x minus 1 divided by 1 over cosine squared of x. So let's try and multiply the top and bottom by cosine squared of x. And we will get 1 minus cosine squared of x in the numerator over 1. So that's going to work out nicely because 1 minus cosine squared of x is equal to sine of x, because that derivates from the identity that 1 is equal to sine squared of x plus cosine squared of x. And after that, we're done, because that is our Pythagorean identity, the first one. So if you don't remember the Pythagorean identities, you want to start with the one that we just used at the end of this problem. And we can divide both sides by sine squared of x first, or divide both sides by cosine squared of x first. And we can get our identity. So one of them is cosecant squared of x is equal to 1 plus cotangent squared of x. And that happens when we divide both sides by sine squared of x. The other one is 1 when we divide both sides by cosine squared of x. And we will get that 1 plus tangent squared of x is equal to secant of x. Right? I find it most helpful, or I guess easiest, to just start with our basic Pythagorean identity, and then to just figure out the other two by dividing both sides by sine squared, or dividing both sides by cosine squared, because sometimes I'll mix them up unless I do that. Okay. Now there is multiple ways to solve this problem. For instance, we could have used the secant squared of x equals tangent squared of x plus 1 identity, and substituted that, the numerator for the start of our problem, in for tangent squared of x, because secant squared of x minus 1 is tangent squared of x. And then we could have simplified that fraction, which is really just sine squared over cosine squared over 1 over cosine squared, which is just sine squared. Then we'd have sine squared is equal to sine squared. So in this case, there's at least 2 ways, probably more ways, to solve this problem. Let's look at the next one. We have 1 over 1 minus sine of x plus 1 over 1 plus sine of x equals 2 secant squared of x. So this problem has 2 fractions on the left side that don't have the same denominator, and I'm trying to equal it to 2 secant squared of x. In this case, we want to use both guidelines A and B, and probably C later on, in that we want to work with the more complicated side first. So the 2 fractions that don't have the same denominators is definitely the more complicated side. So we want to simplify that down. And we also want to combine these fractions into one fraction. Usually, it'll be easiest to solve these problems and show that left side is equal to the right side if we can just have one term on each side. And we know that terms are separated by a plus or minus sign, as long as it's not involved in a fraction. So we have 3 terms here. We want to change this so there's one term on the left side of the equal sign and one term on the right side. So a fraction equal to a fraction. Since 2 secant squared of x is really just 2 secant squared of x over 1. So to do that, we can multiply both of these fractions by the least common denominator, which in this case is just going to be the opposite denominator. So we can multiply the left one by 1 plus sine of x on the top and the bottom. So that way our fractions will combine. All right, we add these together. On the top we get 2 because the sine x and minus sine x cancel. So we have 2 over this denominator. Let's see what happens when we multiply these together. We'll get a 1, a minus sine x, and a plus sine x. So those will cancel. And a minus sine squared of x. We have this equal to 2 secant squared of x. Well, we know that 1 minus sine squared of x is cosine squared of x. So we can change this to 2 times 1 over cosine squared of x, which we know is just 2 secant squared of x, 2 times secant squared of x, right? And that solves our problem. Again, there's probably multiple ways we could do that problem, but that one that we've done here is probably the most efficient and uses the right strategies. Okay, let's look at the next example. We want to see and show that tangent squared of x plus 1 times cosine squared of x minus 1 is equal to negative tangent squared of x. Okay, so in this case, we have 2 binomials that are being multiplied. So that's going to be the more complicated side. So we want to probably change that tangent squared of x into sine and cosine, at least for now, and then multiply it out using FOIL. So we will have sine squared over cosine squared times cosine squared. We'll have a minus sine squared over cosine squared. We'll have a plus cosine squared and a minus 1. And that's the right side we're not changing yet. So that'll become sine squared minus tangent squared plus cosine squared minus 1. Well, if we group the sine squared and the cosine squared, we know that that is equal to 1. So we can change it to 1. Now we have a 1 minus 1. So that becomes 0, and we're left with minus tangent squared of x is equal to minus tangent squared of x. And we're done. We could have multiplied out the tangent squared of x and left it like that for a bit, but we would find that we would need to change at least one of those to sine and cosine. So it helps to do it all at first right away. Next identity, we have tangent of x plus cotangent of x equals secant of x times cosecant of x. All right, so the more complicated side here is technically the left side because we have 2 terms, but in this case there's a lot of different ways you could do this problem. You could change both sides of the equation and change them all to sines and cosines and then start eliminating denominators, and that would probably work fine. Why don't we do that? Let's try to change the left side to cosines and sines and the right side to cosines and sines. Okay, so now we can see here that we'll probably want to have the same denominator as the left and the right side. So we can multiply the top and bottom by both of these fractions by the opposite denominator. So we multiply sine over cosine times sine at the top and times sine at the bottom. So we have sine squared over cosine times sine plus cosine squared over cosine times sine. We can combine those and we get sine squared plus cosine squared over cosine sine. And we know that sine plus cosine is, sine squared plus cosine squared is 1. So we have 1 over cosine sine is equal to 1 over cosine sine. And we're done. Let's see. Oh, we have a similar one here. We have secant of x plus tangent of x is equal to cosine of x over 1 minus sine of x. This is another problem that can definitely be done many ways. Let's try converting the secant and tangent first to sines and cosines. If we do that, we have 1 over cosine of x plus sine of x over cosine of x. We can combine those fractions to get 1 plus sine of x over cosine of x. And at this point, we should have two fractions. 1 plus sine of x over cosine of x is equal to cosine of x divided by 1 minus sine of x. So the best thing here would be to cross multiply for our equation. Whenever we have a fraction equal to another fraction on the other side of our equation, we can multiply the numerator and the denominator that are on opposite sides of our equal sign and set those on opposing sides. So we have 1 plus sine of x as the numerator times 1 minus sine of x as the denominator, and we get a cosine times cosine, so cosine squared of x. And when we multiply out and we FOIL this here, we have 1 plus sine of x minus sine of x minus sine squared of x. So we'll get 1 minus sine squared of x is equal to cosine squared of x. So cosine squared of x is equal to cosine squared of x. And that's it. So I said earlier that there's probably multiple ways to do this problem. And I say that because you could claim that the right side is more complicated, because you have a fraction at the beginning, cosine of x divided by 1 minus sine of x, and that the denominator there has two terms. So you could start instead by multiplying both sides by 1 minus sine of x, and as long as you distribute it correctly, you should get not have so many fractions throughout this process, and it might be a little easier to solve. Right? It'll definitely be a different process, but we should get the same answer. Okay, so now we have, we're going to look at 4 more problems. These are going to be all a little bit different because we're going to have some higher powers of sine, cosine, and tangent, and so on. Okay, so we have the first problem here. This is part F on the document. Cotangent squared times divided by 1 plus cosecant of x is equal to 1 minus sine of x over sine of x. So, and we want to show the left side is equal to the right side. Well, this is a setup where we have that the left side is a fraction, the right side is a fraction, so we can just cross multiply right away. And we might also want to start off having the left side, which is cotangent and cosecant, and only have sines and cosines instead of cotangent and cosecant. So we can change that like this. So we'd have cosine squared of x over sine squared of x times sine of x when we cross multiply equal to 1 plus, well, cosecant is 1 over sine, so 1 over sine of x times, in parentheses, 1 minus sine of x. Okay, and now we've got to do some simplifying on both sides here. So cosine squared of x over sine of x equal to 1 plus 1 over sine of x minus sine of x minus 1, because 1 over sine of x times minus sine of x is going to be minus 1. So we have cosine squared of x over sine of x equal to 1 over sine of x minus sine of x. Well, what do we do here? One thing you always want to be looking out for when you're doing these problems is that you could have the same denominator across all of the different terms. And if that's true, or maybe just have part of a term that's shared in all the different denominators, then it's a good idea to get rid of that by multiplying the numerators by the same term. So here we have two terms that have sine of x in the denominator. So we want to multiply each of these terms by sine of x. And that'll get rid of all the fractions. So we will have cosine squared of x equal to 1 minus sine squared of x after that. All right, we have to make sure that we multiply that by everything. So we will have cosine squared of x equal to cosine squared of x, since 1 minus sine squared of x is equal to cosine squared of x. So if you look at the start of this problem and you just are not sure what to do, the best thing you can do is to start doing things, as long as they're correct, right? And when I say correct, I mean algebraically correct. So you could cross multiply at the start of this problem. You could change everything to sines and cosines. So we did both here. You could try and simplify the denominator on the left side right away, because 1 plus cosecant of x is equal to 1 plus 1 over sine of x. So if you multiply the top and bottom of the left fraction by sine of x, you would already start to simplify your problem. And you could even take your right fraction and split it into two fractions, and you'd be left with 1 minus sine of x minus 1. I'm not so sure that would be helpful to you, but it's certainly something you could try. And, trying something is always important. That's the guideline part E, right? The five guidelines for doing this problem. Maybe what you do doesn't, maybe it doesn't help you simplify your problem, but you don't want to just stare at a problem and not do anything. That's not going to help you. Sometimes even doing the wrong thing will help you see the right thing when you're doing the problem. All right, next problem. We have tangent to the 4x. That's tangent of x times tangent of x times tangent of x times tangent of x equal to tangent squared of x secant squared of x minus tangent squared of x. So the right side is a more complicated side in this one, so we're going to work with that. One of our guidelines for part B is factoring. So whenever we have multiple terms, in this case the right side is two terms, we want to see if they have a common factor that we can factor out. And the hope is that when you factor it out, it'll leave some sort of an expression that we can simplify using our Pythagorean identities, or even odd identities, or reciprocal or fundamental identities. In this case, both terms have tangent squared of x. So when we factor that out, we have secant squared of x minus 1 on the inside. And the key here is to realize that secant squared of x minus 1 is equal to tangent squared of x, using our Pythagorean identities. So we have tangent squared of x times tangent squared of x, which becomes tangent to the fourth of x, right? We add those exponents when we're multiplying bases that are the same. And we're done. Okay, next problem, just two more for this section for 10.2 that will, for examples that we will look at. Let's see, what do we have here? Sine cubed of x times cosine to the fourth of x is equal to cosine to the fourth of x minus cosine to the sixth of x times sine of x. Whew. That is a lot of high exponents. So first thing I'm looking for when I look at this problem is, since we just have two terms here, right, the right side can be considered one term because it's the sine of x is multiplying the whole thing, so they're kind of attached. And I want to say, do each of these share any of the same terms, because if they do, we can divide both sides by those expressions and get rid of them. In this case, they both have a sine of x. So we'll start off by dividing both sides by sine of x. So we have sine squared of x times cosine to the fourth of x equal to cosine to the fourth of x minus cosine to the sixth of x. Well, now we want to look at factoring again, because we have two terms on our right side that are both cosine, so we can factor out the common factor. So cosine to the fourth is the highest common factor, the greatest common factor. So we factor out a cosine to the fourth of x, we're left with 1 minus cosine squared of x. Right, and our left side is cosine squared of x, the fourth of x. I said that wrong. Sine squared of x times cosine to the fourth of x. Okay, and we can divide both sides by cosine to the fourth of x, right? They share that in both terms, kind of similar to step 1. We divide both sides by cosine to the fourth of x. And we're left with sine squared of x equal to 1 minus cosine squared of x. So sine squared of x is equal to sine squared of x. It's using our Pythagorean identity. And we're done. Okay, similar sort of problem. We have cosecant to the fourth of x times cotangent of x is equal to cosecant squared of x times cotangent of x plus cotangent cubed of x. Well, I think the hope is for this problem that we can use strategies that are similar to the last problem and use a similar method to show that left side is equal to right side. Here is probably one time when it's probably not really helpful to change everything to sines and cosines, because we might just be able to deal with this without having to do that, right? We can divide both sides first by a common factor here, because we have a term equal to another term. There's just one term on each side. They both share cosecant squared of x. So if we divide both sides by cosecant squared of x, we are simplifying our expressions. And we're left with cosecant squared of x times cotangent of x equal to cotangent of x plus cotangent cubed of x. And once again, the right side both share a factor, cotangent of x. So we can factor that out, and we're left with 1 plus cotangent squared of x times cotangent of x. We can divide both sides by cotangent of x, because they both share that on the left and right side. So we have cosecant squared of x is equal to 1 plus cotangent squared of x, and that is one of our Pythagorean identities, that 1 plus cotangent squared of x is equal to cosecant squared of x. And we're done. Okay, so that's a lot of examples of using all our different tools. Right, some of your homework problems has problems like these, or homeworks that we have in the future. I'm going to continue straight into the next lesson. So if you're at this point in the video and you've been listening, we're about 28 minutes in, I would say maybe take a break, maybe look at the homework, see if you can solve any problems, do something else, and then come back at about 28 minutes. But I'm going to make this one big video for this section. Okay, for the next section, for chapter 10.3. Chapter 10.3 for pre-calculus here is basically just using more tools to solve for x in equations. So before we have been showing that the left side is equal to the right side, but now we have a left side and a right side, but we want to know when that left side and right side are equal. For what values of x are they equal? So it's a little bit different. We'll basically just look at a number of examples, and I will have a number of problems with solutions that you can try on your own, and then look up the solutions later. They're not problems I'm collecting. I will just be collecting the homework when we get back for school in session, whenever that may be. So let's just jump right into examples and look at what tools we're using here. So the first one, we have sine of x plus square root of 2 is equal to minus sine of x. Okay, and we're trying to figure out what value of x would make this equation true. So if we plug in something like, let's just try something in our heads, right? 30 degrees. If we plug it in for x on both sides, we want to see if that would be true. So sine of 30 degrees is 1/2. So we would be getting 1/2 plus square root of 2 is equal to minus 1/2. Right? That doesn't work. So we need to use methods to simplify this down so that we can figure it out without guessing. So how do we do this? Well, just like solving for x, we want to, one, have like terms on and combine those together, or in this case, we want to make sure all the x terms are on one side of the equation so that we can do something with them. For here, if we add both sides, if we add sine of x to both sides, we get sine of x plus sine of x plus square root of 2 is equal to 0. And we're just going to throw that square root of 2 on the other side by subtracting square root of 2 on both sides. And we have 2 sine of x is equal to minus the square root of 2. So sine of x is equal to minus the square root of 2 over 2. So now we got to think about our unit circle. If we draw our circle, we have to pick the x value where we have to pick the input variable when our y coordinate on the unit circle is minus square root of 2 over 2. So in this case, I guess these problems that are using x as an input variable are not very helpful, because really when we're thinking about when we're thinking about sine, we're thinking about the y coordinate, not the x coordinate. So it can be a little deceiving. So what is our y value where the y coordinate is minus square root of 2 over square root of 2? Well, if you think about it, there should be two places. One is at 225 degrees. The other is at 315 degrees. Right? Since it's a circle, there's always going to be two coordinates where you can get these values. So what matters for these problems is the range of the function. Right? For a degree, you can take sine of any degree, but you are never going to get an output. You're never going to get two different outputs on a calculator, right? In this case, we consider sine to have a range. Let's see. If we're plugging in an angle and we're getting a y value, I guess we're thinking about the domain. Yeah, we're actually thinking about the domain. So what angle is it going to spit out for here for the x value? Right? Because we're trying to figure out the input, not the output. We know the output is minus square root of 2 over 2. So a helpful hint is that it's never the third quadrant. Both sine, tangent, and cosine do not have inputs of the third quadrant. So in terms of our solution here, we can rule out 225 degrees. That's not going to be it. So what we will say is that sine's domain will be the angles in quadrants 1 and 4. Actually, the reason that we're confusing ourselves here is we're actually using inverse sine. So once we have sine of x is equal to minus square root of 2 over 2, we want to take the inverse sine on both sides. Sine inverse of minus square root of 2 over 2. So we're getting x is equal to the inverse sine of minus square root of 2 over 2. Okay, that makes more sense because normally sine and cosine and tangent, you can plug in any input value. Well, for tangent, you can't plug in values where you would end up dividing by 0. But for the inverse functions, we consider that their output values have a limit. Okay, that makes more sense. So the range is restricted to either quadrant 1 or 4 for sine. For cosine, we'll say, for inverse cosine, we'll say that the range is either quadrants 2 or 3. And for tangent, we'll say that the range of inverse tangent is going to be either quadrants trying to remember here. I think it's also quadrant 1 or 4. Let's see here. Don't want to. I'm just checking just to make sure I'm not saying this wrong. Yeah, so that's right. So quadrants 1 or 4 for tangent as well, for inverse tangent. Okay. So we're going to be using these a lot for pretty much any time you're solving for x. For these problems, it's always attached to sine or cosine or tangent or something else, which means to get x alone, you have to use the inverse tangent. And you can do the problem without doing that. You can say, what angle, when you plug in, do you have to plug in for sine, is it equal to this value? That's what we were doing at first, but it will confuse you because when you think about sine, you can put in any angle to sine and you will get an output. But we are restricted when we're solving for x like this, right? We're missing something when we are not thinking about the inverse functions. So for sine inverse of minus square root of 2 over 2, the answer will be that x is equal to 315 degrees. That is the same as 7 pi over 4 radians. And sometimes you will see that really you could say any multiple of 315. So if you said 730 degrees, oh wait, that's not right. By multiple, I mean when you add 360, because if you go around a full time in the circle, you will get 675 degrees, which is really just 315 degrees at the same spot in the unit circle. And you can represent that by saying 315 degrees plus 360 degrees times n, where n is an integer. Or for radians, you could have 7 pi over 4 radians plus 2 pi n radians, where n is also an integer. For me, I am fine if you just say, if you just give one angle that's within the correct range, and you don't have to add the plus 360 degrees times some integer. That's fine. All right, let's look at another problem here. So the second one we have is 3 tangent squared of x minus 1 is equal to 0. So we're going to try to get that x alone. So let's add 1 to both sides and then divide both sides by 3. And now we have tangent of x times tangent of x is equal to 1/3. So it will be perfectly fine to square root both sides, get rid of that square value. The square root of 1/3 is the same as the square root of 1 over the square root of 3, which is the same as 1 over the square root of 3. And if you multiply both the top and bottom by the square root of 3, you get the square root of 3 over 3. So at that point, we have tangent of x is equal to the square root of 3 over 3. We can take the inverse tangent of both sides, which will leave us equal to, we'll have x all alone. X is equal to inverse tangent of the square root of 3 over 3. So for tangent, we got to think about on a unit circle what two values for x and y for our coordinates. When you take the y value divided by the x value is equal to the square root of 3 over 3. So we know that square root of 3 over 2 and 1/2 are x and y values that match together. as well as the square root of 2 over 2 and the square root of 2 over 2. And 1 and 0, right? We have coordinates of 1 comma 0 at 0 degrees or 2 pi degrees, and 0 comma 1 at pi over 2 degrees, which is 90 degrees. Okay, and if we're trying to find some combination of these three possible x and y coordinates, right? The only square root of 3 that appears is for those multiples of 30 degrees. So we want either square root of 3 divided by square root of 3 over 2 divided by 1/2, or 1/2 divided by the square root of 3 over 2. So if you work out the math here, the square root of 3 over 2 divided by 1/2 is just the square root of 3. So that can't be it. While 1/2 divided by the square root of 3 over 2 is equal to 1 over the square root of 3, which is equal to the square root of 3 over 3, right? Because we did that math earlier. Okay, so we want a coordinate where we are taking our y value of 1/2 and dividing it by the x value of the square root of 3 over 2. Okay, where x value, we're moving the square root of 3 over 2 in the x direction, and just that 1/2, that would be 30 degrees. So x is equal to 30 degrees, and that is within our the range of inverse tangent, right? The range of inverse tangent is quadrants 1 or 4, which, and 30 degrees is in quadrant 1. The other possible answer that you might be tempted to choose would be quadrant 3, because it's also true that you could get square root of 3 over 3 if both terms were negative, and then the negatives would just cancel out. So, but we know that inverse tangent does not accept that as one of its valid ranges. Okay. And the reason for that is I've realized that we've not looked at the graphs of inverse tangent, or inverse secant, or inverse cosecant. So what I would do is, it is a lot easier to look at one of these up instead of trying to graph it. So I would pause the video now and go over to Desmos and try to graph. You can type it in as arc tangent, or I think it'll also accept cotangent, tangent raised to the -1, right? That's the kind of notation, another notation for inverse tangent, and seeing what that graph looks like. And you'll see why a range of, what would that be? Opposite of 30 degrees would be 210 degrees. And you'll see why a range of 210 degrees, or if you're doing it in radians, then that would be 7 pi over 6. Why that's not a viable thing, right? It shouldn't reach that y value. It also depends what way do you choose the x and y axes. Sometimes you'll see graphs of inverse tangent, or inverse cotangent, or inverse cosecant. You'll see that they will switch up the axes and make it so that the input values are the coordinates on the circle, or for tangent, like square root of 3 over 3, that's a combination of two coordinates, and the output is an angle. Right, so the graph will look, it will be a reflection about that line y is equal to x if they choose to do that. So you do have to pay attention to the axes and figure out what in the world or which way they're deciding to graph that, because it'll look different, certainly, depending on that. Okay, the way it should be graphed is having the values on the x-axis as the independent variable, and the output variable should be the angle, right? Because our range is restricted for the inverse functions. Anyways, so we get an answer of 30 degrees. All right, let's try and work through a few other problems and show some strategies we can use. The next one says cotangent of x times cosine of x is equal to 2 cotangent of x. So we can first simplify down by dividing both sides by cotangent of x. And we get cosine squared of x is equal to 2. We can square root both sides and then take the inverse cosine of both sides. So we're trying to find, well, when is it that for x, let me say this differently. For what angle does it correspond to an x value of the square root of 2 on our unit circle? Well, the square root of 2 is equal to 1.414, etc., etc. And if we're talking about the unit circle here, then we have an issue because that is outside the circle's domain, I guess we would say. So if you, on a calculator, say arc cosine of the square root of 2, oh wait, my calculator's not working. Please work. Technical difficulties, I guess. Google has failed me as a calculator. I'll have to go to Wolfram Alpha. So let's try this again. Cosine, we're going to try cosine inverse, or arc cosine, of the square root of 2. Okay. Wolfram Alpha gives you a lot of information that we really don't need. Here it is. Okay. So it almost appears like it gives you an answer, which has had me confused. It doesn't outright tell you that it's outside the range. Instead, it gives you an imaginary number. So instead of saying, this is not within our domain, what are you doing? It gives us an imaginary number, so it kind of hides that. So what we should write for this is that this answer is going to be no solution. No solution. So there is actually no value of x that we could plug in to this equation and make it true. So perhaps the easiest one would be thinking about cosine of x is equal to the square root of 2. So what angle produces an x coordinate on the unit circle equal to the square root of 2? And there's none of them because square root of 2 is a larger number than the radius of the circle, right? If we go and find the very largest number on our circle for the x coordinate, it's 1. That's at 0 degrees or 2 pi or 2 pi radians. Square root of 2 is beyond that at 1.4. So there's no solution here. So if you have a calculator and you have it in the right mode, actually for arc, for the inverse tangent functions, it doesn't matter if it's in degrees or radians. It should say it's undefined, because both for degrees and radians, you use the same coordinates of the circle. But in any case, you should get a no solution for here. So you have to be careful of the domain in this case of the inverse functions. All right, let's jump to the next one. We have 2 sine squared of x minus sine of x minus 1 is equal to 0. So here we're going to try and factor this like it is a quadratic equation. So sometimes I find it helpful to not think about all these signs and just use a variable instead. So if we set z equal to sine of x, this would be equivalent to 2z squared minus z minus 1 is 0. And now we're trying to factor this like we would a normal algebraic equation. So we want to look at if we multiply 2 and minus 1, and then we add it, and if we add 1 times plus 1, would that equal to minus 1 for z? Right, we have to consider the a constant and the c constant, and then the other factor, because you could have 2 times 1 to get 2 for the coefficient of z squared, or you could have negative 2 times negative 1, but also you can multiply and get minus 1 times to either be minus 1 times plus 1 or positive 1 times minus 1. And when you add those two combinations together, it doesn't equal minus 1. So here's how I might do the work for that. I would have 2 times minus 1 is, and if you add plus 1 times positive 1, is it equal to minus 1? And we do that work, and we get, that should be equal to 0. So no, that doesn't work. If we do another combination, let's try 2 times positive 1 plus 1 times negative 1. Does that work? Well, we would get positive 1. So that doesn't work either. If we did, let's see, what have we not done? Oh, what if we had negative 2 and negative 1? And we had 1 and negative 1. Add those together. That would be, minus 1. So we want to have a minus 2z, and on the other side, a minus 1z, with we want that to be multiplying a positive 1, so 2z minus 1 and a minus 1z minus 1 equal to 0, which is the same as minus 2z minus 1 times minus z minus 1. We plug back in the signs, so we have minus 2 sine of x minus 1 minus sine of x minus 1 is 0. Okay, and now we have to use the zero product property here. All right, we set the left side equal to wait a second. Did I do this wrong? Ooh, I did do this wrong. I used a plus 1. There. It should be a minus z plus 1. Okay, I was double checking my work while I was talking. So we had plus z and a minus 2z, so that gives you minus z. Okay, there we go, that fixes it. Okay, so we have minus 2 sine of x minus 1 minus sine of x plus 1. Okay, let's bring this out and use the zero product property. So we should get 2 answers here, right? Minus 2 sine of x minus 1 is equal to 0, and minus sine of x plus 1 is equal to 0. So we have minus 2 sine of x is equal to 1. So we want to find x when sine of x is equal to negative 1/2, and also find x when sine of x is equal to 1. So if we take the inverse of both sides, we get x is equal to the inverse sine of negative 1/2, and x is the inverse sine of 1. Okay, so for minus 1/2, we want to find the y value, or we want to find the angle that produces a y value of minus 1/2. So let's do minus 1/2. If we think about a unit circle, that is either at 100 or 210 degrees, or that is at 330 degrees. So we know that the range of inverse sine is quadrants 1 or 4, so it has to be 330 degrees, right? It can't be, because it can't be anything in the third quadrant. And for the inverse sine of 1, Well, where is the y value equal to 1? Well, there's only one spot, right? It only reaches its max height of 1 at an angle of 90 degrees. Right, that's 0, 1. So x would be equal to 90 degrees here. So we have two answers. X can be equal to 90 degrees or 330 degrees. Or you could list those as radians as well. So for this particular problem, right, we gotta use some factoring skills, the zero product property, and thinking about how we can evaluate inverse sine or cosine functions of values and producing an angle from that. Okay, next problem. We are on part E here. So we have 2 sine squared of x plus 3 cosine of x minus 3 is equal to 0. Okay, so we looked at an example like this. I guess it was last week on Thursday or Wednesday, where we had two different trig expressions, and we were trying to factor this in some way. And we can't factor it unless we have the same trig expression. It's almost like having different variables in this case. So we want to convert that sine squared of x to cosine, if possible, which we can do because we know that sine squared of x is involved in one of our Pythagorean identities, and it would be equal to 1 minus cosine squared of x. So we can plug that in for sine squared of x. And then we got to do some simplifying. Okay, so we'll have an extra 2. So we get that 2 times 1. And that will combine with the minus 3. So we have minus 2 cosine squared of x plus 3 cosine of x. Minus 1 is equal to 0. Okay, more factoring. I don't like all these negatives, so for this one I'm going to divide both sides of the equation by negative 1. So we get 2 cosine squared of x minus 3 cosine of x plus 1 is equal to 0. Right? Dividing 0 by negative 1 isn't going to do anything to it, so we can do that. So this time it's a little bit easier if we do that. We just got to find two factors when we multiply them together that add to a total of minus 3. So one easy way to do that is if we add minus 2 and minus 1, we'll get that. So we know that we could use minus 2 cosine of x plus 1 times minus cosine of x plus 1 equal to 0. Let's see, does that work? We get a minus 1 cosine of x and a minus 2 cosine of x. That becomes minus 3 cosine of x. That works. And we get the plus 1 for our constant. You could have also done this as 2 cosine of x minus 1 times cosine of x minus 1 and gotten the same thing. So it will ultimately not change our answer. We can use the zero product property and get two equations. Minus 2 cosine of x plus 1 is equal to 0, and minus cosine of x plus 1 is equal to 0. So minus cosine of x is equal to minus 1. Cosine of x is equal to 1. Oh, sorry, I'm doing the right one first for no good reason. X is equal to the inverse cosine of 1. So x is equal to, well, we want to find the angle that produces an x value of 1 for cosine here. Well, there's only one spot we can get an x value of 1, and that's at 0 degrees or 2 pi degrees. I'm just going to say 0 degrees, but you could put 2 pi degrees if you wanted. For our left part of the zero product property, we have minus 2 cosine of x is equal to minus 1. So we get cosine of x is equal to 1/2. So x is equal to the inverse cosine of 1/2. So what angles produce an x coordinate of 1/2? Well, that's only that's less than the square root of 3 over 2. as we approach 1. So it's not going to be 30 degrees because we have to move square root of 3 over 2 to the right to get to 30 degrees. This is either going to be 60 degrees, or it's going to be, if you think about moving the positive x direction in quadrant 4, that would be 30 degrees plus 270, so that's 300 degrees. But we know that the range of inverse cosine is either quadrants 1 or 2, which eliminates 300 degrees. It means it can only be 60 degrees. So we would say that x is equal to 0 degrees or 60 degrees. And whenever you get multiple answers like this, it should be true that if you plug in 0 degrees and you do the math, you get that the left side is equal to the right side, but that it also works for your other answer or other answers. Now, the reason for that, in this case, like if you have something equal to 0, it's very easy to check. If you were to have a graph of this, you should see that if you were to plug in that x value, that your output would be 0, right? That means that your graph is crossing the axis at it's crossing the y-axis at 0, or an x input of 0 degrees and an x input of 60 degrees. So I have not graphed this equation, but I suspect if you were to put it in a Desmos, that is what you would see. That's what these solutions are talking about. Okay. A new way to solve a problem here would be good to look at. We have cosine of x plus 1 is equal to sine of x. We don't have any squareds or anything. So we can't just convert, cosine of x plus 1 to sine of x, because that's not true. But we want to have those squares, otherwise we can't really do much of this problem. So what we're going to do is square both sides of our equation here, raise both sides to the power of 2, and then we'll go from there. So we have cosine of x plus 1 squared is equal to sine squared of x. So we have cosine squared of x plus 2 cosine of x plus 1 is equal to sine squared of x. Well, what can we do here? I think one thing we could do is we could change that sine squared of x to be in terms of cosine. If we do that, we would get that cosine squared of x plus 2 cosine of x plus 1 is equal to 1 minus cosine squared of x, and then we can combine some like terms. So we get 2 cosine squared of x plus 2 cosine of x. The 1's will actually cancel here, is equal to 0. So here we're going to do some factoring. 2 cosine of x is a common factor. And in the parentheses, we'll have cosine of x plus 1 is equal to 0. This again is the zero product property. We have 2 cosine of x is equal to 0. And we have cosine of x plus 1 is equal to 0. So we have cosine of x is equal to 0 for the left one. So x is equal to inverse cosine of 0. So what angle produces an x value of 0? Well, there's two. There's either at the top of our unit circle 90 degrees or the bottom at 270 degrees, but only 90 degrees is in quadrants 1 or 2. So our answer here has to be 90 degrees for this part. For the right side of the zero product property, we have cosine of x is equal to minus 1. So x is equal to inverse cosine of negative 1. So when is our x value minus 1? Well, it's only at one spot. It's at 180 degrees. So our answer here is either 90 degrees or 180 degrees. Okay. The next two problems use something called multiple angles, where we have not just cosine of x, but what if we have cosine of 3x? As in cosine of parentheses 3x. Whatever our input is being multiplied by 3. So here's our problem. 2 cosine of 3x minus 1 is equal to 0. All right, let's simplify what we can. We can add 1 to both sides. We can divide both sides by 2. So we have cosine of 3x is equal to 1/2. Now, if we take the inverse cosine of both sides, we can still do that. We have 3x is equal to the inverse cosine of 1/2. Now we just divide both sides by 3. So in this case, the multiple angle problems is really just one extra step if we are using inverse functions. So what angle produces an x value of 1/2? Well, I think we just did this. I think it was 60 degrees. So x is equal to 60 degrees, but now we have this divided by 3. So our answer will be x is equal to 20 degrees. So hopefully not too bad, just one extra step there. Let's try it again, but now x is, for this problem, is being divided by 2. So it's tangent of x divided by 2 plus 3. We can simplify by getting rid of those 3's. Subtract 3 on both sides. Divide both sides by 3. So we get tan of x over 2 is equal to minus 1. We can take the inverse tangent on both sides and then multiply both sides by 2. And we'll have 2 times the inverse tangent of minus 1. So what y and x value when divided is equal to minus 1. So if we remember the what would this be? The range of inverse tangent is quadrants 1 or 4. And there's only one of those quadrants that produces one coordinate that's positive and one that's negative, and that's quadrant 4. So we know we have to think about quadrant 4. And to get negative 1, that means that we are dividing the same value by it's a negative value, which would be at 315 degrees, because the coordinate there is the square root of 2 over 2, comma, the negative square root of 2 over 2. So when we divide y by x, we will get negative 1. So we're getting 2 times 315 degrees. Well, isn't that peculiar? We get 630 degrees. So our answer we get when we simplify is actually bigger than 360 degrees. Could you leave it like that? Sure. I would say you can, as long as it's asking, as long as it has the problem is asking you for a more specific answer. But oftentimes it'll say, what is x equal to within the range of 0 to 2 pi, or 0 to 360 degrees. In that case, you need an answer within 0 to 360 degrees, and 630 is way above, so you need to subtract 360 degrees until a certain number of times until it's within that range. So if we subtract 360 degrees, we get 270 degrees. Let's see, we double check that math. Yeah, that's right. So if we go back to our equation, it should be true that if we plug in 270 degrees to x here, that we will get the left side equal the right side. Let's see. I'm going to check my work here. So 3, let's see, tangent of 270 over 2. So that's tangent of, what divides that? 135. 135. Tangent 135. Oh. Well, tangent of 135 is one of our common angles, so that's good. Tangent of 135 would be minus 1, because the x and y values there are minus square root of 2 over 2, comma square root of 2 over 2. So 3 times minus 1 plus 3 is equal to 0. So minus 3 plus 3 is equal to 0. Okay, good. We did do it right. We get 0 is equal to 0. So our answer is x equal to 270 degrees. Or if you're doing this on the radians, also fine, that would be 3 pi over 2 radians. I have one last problem that we'll look at together. We have secant squared of x minus 2 tangent of x is equal to 4. Well, same issue as before. We can't really combine these in any way since secant and tangent are different. So let's try and convert secant to tangent, which we can do luckily because secant squared of x is equal to, I believe it's equal to 1 plus tangent squared of x using the Pythagorean identity. Now this sets us up nicely for using the quadratic formula or factoring. I guess for most of these we always want to factor. We have tangent squared of x minus 2 tangent of x minus 3 is equal to 0 once we move the 4 over. And now we just need to factor tangent of x. Let's see, if we do a minus 3, then we could have tangent of x plus 1 equal to 0. That'll give us a minus 3 tangent plus a positive tangent, and that will be a resultant of minus 2 tangent. Right, zero product property, again, tangent of x minus 3 is equal to 0, and tangent of x plus 1 is equal to 0. So tangent of x is equal to 3, and tangent of x is equal to minus 1. So x is equal to inverse tangent of 3, and x is equal to the inverse tangent of minus 1. Well, for minus 1, I think we just did that. The inverse tangent of minus 1 was 315 degrees. So x could equal to 315 degrees. What about the inverse tangent of 3? When does the x value, or the y value, divided by the x value equal to just 3? There's no square roots here. Well, that means that our y value is 3 times bigger than our x value if we were to get 3. Well, off the top of my head, I certainly don't remember any of our common equation coordinates. So that probably means that this is going to be a decimal. We need to use an external calculator to figure this out. So let's do it. Arc tangent of 3. What is this equal to? Okay. So when I put it in Wolfram Alpha, it says that this answer is approximately 71.57 degrees. 71.57 degrees, right? That is not one of our common angles, but it is a valid answer, funny enough. This form of this answer can usually be written as some form of irrational numbers, kind of added together in some strange function, but it is certainly not easy to find with what we have now, at least. Yeah. I was looking at some other data, but we're not going to go into that. You can just leave it as that angle. So we have two answers, 71.57 degrees or 315 degrees for this last problem. Okay, well, that's a lot of examples, a lot of different tools. If you reach this point, congratulations. You're probably one of the few students that is still listening. Hopefully, I would love for you all to be listening. But it is a lot of problems, a lot of time to listen. This is probably the one lesson that we'll use for these next 2 weeks. If we have longer than 2 weeks, I'll definitely post another video. The practice problems are listed on the sheet, the notes sheet. There's 14 of them. So if you'd like to practice those, you can do that. These are similar problems to the last 9 that we just did. And then I will have the answers to those as well. post it at some point. Maybe not today. I'm running short in time. All right. Well, the homework will be collected when we are actually back in session, whenever that may be. If it is in 3 weeks, then great. If it's extended longer, then I guess we will see. But that's it. Yeah, smash that subscribe button. Okay, bye.